then you would have the power series, right? I would just give you the formula for that function, give you the formula here, and now you have its power series. So we're going to develop how you get from here to those things, right? That's what I'm saying here. So let's say we're given, I'm ready to start the development, given some function, right? Suppose, that's the suppose symbol. Suppose it has a power series. So I don't know what it is, okay, but I'm just saying suppose it does, right? Suppose it has a power series. Then I could write this. Then I could say that the function, the original function, is the sum n equals 0 to infinity of c sub n x minus a to the n. Because I'm saying that the function I've been handed has a power series. I just don't know what it is, right? So there. Now, because of where I'm about to go with this, I'm going to write out about 5 of these. This is c sub 0 plus c sub 1 x minus a plus c sub 2 x minus a squared plus c sub 3 x minus a cubed plus c sub 4 x minus a to the 4th plus c sub 5 x minus a to the 5th plus dot, dot, dot. That's what it is, right? Further, I said, and you agreed with me just a second ago, I would love to have a formula for that, right? If I had a formula, if I just had a formula, then I'd have the power series. Well, having the formula, maybe I can figure out the formula if I can figure out what these are, right? I mean, that's really all I need to do is figure out what are those numbers? What are those numbers? What are they, right? So Taylor said, all right, I'm going to go find them. Here's how. First thing Taylor said is, let's take the derivative of this. Take the derivative. What's the derivative of this function? Don't give me the formula here. Give me it out here. So you would have 0. Then here you'd have c sub 1. What? That's it, right? C sub 1 plus c sub 2. The 2 came out in front. 2 c sub 2 x minus a plus 3 c sub 3 x minus a squared. Yes, yes? I'm going to stop. I'm going to keep going. Right? That's no, I need more. Sorry. I need more for where I'm going. Apologize. I know this is ridiculous, but just hang in there, okay? Let's go that far. So that's the derivative, right? Remember, Taylor's sitting here going, all right, I need to try to see if I can come up with a formula, a generic formula. So he said, all right, let me at least just try and find that guy. If I can just find the first constant, right? Right, the first constant, maybe I can, or just any of these, right? So looking at that derivative, what would happen if you plug what would happen if you plug a into the derivative? What would you get if you plug a into the derivative? This is the big light bulb moment. You get c sub 1. Because every other term goes away, right? So you get c sub 1. So you actually just gave me exactly what c sub 1 has to be. C sub 1 is just the derivative of that function that we were given evaluated at a. We've got one of them, right? I need to back up. We didn't get c sub 0, right? Using the same methodology here, how could you find c sub 0? If this is your original function, how could you find that? Plug what into this function? Plug what into this?
Well,
if you plug in a, right? So go back up to this, just insert a little line here. If I plug in a into that function, what happens? 0, 0, 0, 0, 0. The only thing left is c sub 0, right?
Yeah.
So check this shit out. What we're saying is C sub 0 is just the function evaluated at A. And C sub 1 is just the derivative of the function evaluated at A. Right? And now you're thinking, okay, so C sub 2 is probably the second derivative at A, right? Not quite. It's close, but it's not quite. All right, watch. To do it, we're going to take the derivative a second time. Okay, I'm going to take the derivative a second time. So if I take the derivative again, derivative constant is 0. Okay, here, what's the derivative of this? 2c sub 2. And then derivative of that? 6c sub 3 x minus a. Next one? 12. Yeah, so you know what? Because I know where I'm going with this, is it okay if I don't write 6? Are y'all okay with me writing, instead of 6, 2 times 3? And on the next one, instead of me writing 12, is it all right if I write 3 times 4, x minus a squared? And then on the next one, instead, I'm going to write 4 times 5, c sub 4. Ah. Okay? Now, use the same approach. Plug a into this. What's the second derivative at a? 2c sub 2. 2c sub 2. Not c sub 2, it's 2c sub 2. So what do I need to find c sub 2? Divide both sides by 2. Right? So let me kind of put a list. It's going to be off camera, but this is what I have. I have that c sub 0 is the function at a. I have c sub 1 is the derivative of the function at a. I have c sub 2 is the second derivative of the function at a over 2. Right? And now I'm going to go again, and I'm going to do the derivative a third time. So what's the derivative this third time? Third derivative. Okay, we're taking derivative of this now, right? Okay, so derivative of 2c sub 2, 0. Derivative of this, 6. I'm going to write 2 times 3, c sub 3. Derivative of this, 2 times 3 times 4. 2 times 3 times 4, c sub 4, x minus a to the first power. This one, 3 times 4 times 5, c sub 5, x minus a to the second power. Plus, and it keeps going, right? Now plug 0 into the third derivative. What do you get if you plug 0 into that? 2 times 3 c sub 3. And so now solve for c sub 3. You've got to divide both sides by 2 times 3. So the third constant, c sub 3, is the third derivative at a over 2 times 3, right? Why not? So what's the next one going to be? So this will be the fourth derivative at a over 2 times 3 times 4, right? Which is 4 factorial. Yes. Right? Look at, this is really 3 factorial. All of these have a 1 next to them, don't they? Yeah. So this is 2 factorial. This is 3 factorial. If we do it again, we're going to get 4 factorial. If we do it again, we're going to get 5 factorial, 6 factorial. Do y'all see that each time we do a derivative, we keep building the factorials up? Wait, where am I? Up here. On the next derivative I take, right, what are we going to have as our constant? 2 times 3 times 4. When we differentiate over here, we have 3 times 4 times 5, right? But when we take that derivative, that 2 is going to come out. And now in the next time through, it'll be 2 times 3 times 4. I can't even say it. 2 times 3 times 4 times 5. Right? This one, well, I don't have it, right? Do y'all see? Freaking beautiful. All right, so we have a formula. We have a formula because we have a pattern, right? We have a pattern developing over here. The formula is this. if you want to know what C sub n is, then what you're going to have to do is take the nth derivative and then plug a into it. And divide that by what? N factorial. And this is the master, like, this is it. Because every function, most functions, almost all functions can be written in a power series. And the only thing you have to do to determine what its power series is determine what those constants are. And this is a formula to find the constants. And it requires that you're able to take successive derivatives. That's the only real requirement, is that these derivatives exist. So I want us to go back and I want us to look at the sine function that we just did a second ago. And I want to see if we can come up with the power series, for that. So if f of x equals sine x, find a power series about x equals 0. I'm going to write that formula that we just developed right here on the board. C sub n equals the nth derivative at a over n factorial. So I need to be able to take successive derivatives of this. Can we take derivatives? Yes, we can, over and over and over. And then what I need to do is plug in the value of a into each of those derivatives and then divide by the factorial. Yes?
I was going to say, since you know that like the whole sine derivatives are cyclic at some point, can you do anything with that?
Yes, we can. You'll see. It's going to happen. All right, so here's the standard approach for these. The standard approach is that you're going to make kind of like a table, all right? What you're going to have here are you're going to write down what f is, then the derivative, then the second derivative, then the third derivative, then the fourth derivative. And you need to go as far as you can, as far as you need to go, either to see a pattern establish or to get a formula for the nth derivative. This is the derivatives, and then what you want to do is for each of those derivatives, you want to do, the plug-in at x equals 0. So we want to do each of those derivatives at the value of 0. So what is the value of the first? What is the original function? Sine x. Okay. All right. What is its derivative? Okay. We've been through this, right? So I'm going to go quickly. I think I'll do 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. There's 8. Went through the cycle twice. Now what happens when I plug 0 into each of these? Sine of 0.
1.
0, right? Sine of 0, 0. Cosine of 0, 1. Sine of 0, 0. Negative cosine of 0, negative 1. Sine of 0, it's going to repeat now, right? And that's just keep repeating itself, right? So now what I'd like to do is I'd like to write down what the C's are. Okay, so if we're keeping track of things, these are all the derivatives, right? These are all my derivatives. These are all the derivatives at x equals a. In this case, a is 0. And the next thing I'm going to do is I'm going to find what C sub 0, C sub 1, C sub 2, C sub 3, C sub 4, C sub 5, C sub 6, C sub 7. I don't know how many of these I'm going to need. What is C sub 0 using this formula? It's what's the top? It's the 0th derivative, right? 0th derivative, which is the original function at a. So this is the original function at 0 divided by 0 factorial. What's the original function? What's the original function? Sine at 0? 0. So it's 0 over 0 factorial, which is 0. What's c sub 1? It's the first derivative, right? First derivative, plug in 0. First derivative, plug in 0, and then divide it by 1 factorial. What's the first derivative at 0? 1. We just got that right here. 1 over 1 factorial. The next one is the second derivative at 0, which is really just what? That number right there, right? So the numerators of all these fractions, the numerators of these fractions are just these from this list, right? And the denominators are just factorials. So it'll be 0 over 2 factorial, right, which is 0. The next one is, what's the C3? Negative 1 over 3 factorial. I'll just leave it. Fourth one is 0 over 4 factorial. And then next one, 1 over 5 factorial. Then 0 over 6 factorial. And the last one would be negative 1 over 7 factorial. I feel like I'm running out of time. So I have all the constants, right?
Yes.
Well, at least the first 8 of them. So what we were saying is, can we find a power series for this? And the answer is, well, if I can take derivatives and then plug in the place we're doing the series about, so plug in 0, then that should help me build the constants up, right? And now I can just plug into the power series. So let's do that. I don't want to have to write it all again, but I'm going to, just so I have something to reference. Remember, we're saying we think that this function has a power series. And we think the power series looks like this. Right? That's what the generic power series should look like. And we just found all the C's. And then we know what A is. For us, A is what? 0, right? So what we're saying here is that the sine function should be c sub 0, which we said was 0. I'll put it here. Plus c sub 1. C sub 1 was what? 1. And then x minus 0, right? X minus 0 is just x. So just 1x. And then plus c sub 2. C sub 2 is 0, so that whole thing's gone. Don't care about it. Plus, okay, c sub 3. C sub 3 was negative 1 over 3 factorial, right? X minus, or not x minus, what was it? X minus 0, right? Yes. So x minus 0 is just x to the third power? X cubed. Plus, okay, c sub 4. What's c sub 4? 0. Plus, now c sub 5, which is 1 over 5 factorial. X to what power? Fifth, because we're at the fifth one, right?
These are all odd powers.
They're all odd powers. And in pre-cal, you learn that sine is an odd function. And cosine is an even function, right? And the reason actually has to do with the series, not with anything else. So a function is even if it's got an even power series and odd if it has an odd. Yes?
So for this one, we don't have a constant. That's why like sine starts at 0. And cosine, it's the even function, and it's shifted up 1, so it has a constant.
Yep. So if we do cosine the same way we just did this will be a 1. Yep. Okay, I need to keep going. C sub 6, that's 0. And then the next one will be plus, and then we have the negative 1 over 7 factorial x to the 7th. And then plus dot, 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 right? I'm going to clean this up. Sine x is equal to x minus 1/6, no, I'll leave it. 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh plus, any guess to the next one? 1 over 9 factorial x to the ninth and so on and so forth, plus, plus, dot, dot, dot. There it is. That is the power series centered at 0 for sine. And you can verify for yourself that this is 1 over 2n minus 1 factorial x to the 2n minus 1. So if you write that in sigma notation, oh, I'm forgetting a very important thing. Negative 1 to the n. Sorry, it alternates. So this makes it alternate, starts positive, then negative, positive, negative, positive, negative. And then this right here are your odd numbers starting at 1, and then raising to odd numbers starting at 1. Check for yourself that that works. Where are our formulas? We've now made it to this formula sheet that's only coming up sideways, unfortunately. It looks upright to you? All right, so if you look here, right, on that sheet, I have highlighted here sine x. You see I have sum n equals 0 to infinity of negative 1 to the n, x to the 2n. I used minus 1. Uh-oh, hold on. Oh, we started at 0. I'm sorry. This is my fault. We started at 0. Remember we were starting at 1 before? So this has to be plus 1. Otherwise, we're going to get negatives, and that's not what it is. Plus 1, plus 1. I'm glad I looked at this. All right, so you can see there that that gives you that series. The rest of these functions on this table, you could do the same way. You could try and come up and make a table of all the derivatives, plug in the 0. Yes?
I think you can rotate it by clicking view.
View. See, this is OneNote. So in OneNote, it doesn't work the same. Trust me, OneNote for some reason makes this really hard to rotate. It's an inserted PDF, so it doesn't let me rotate it the way that I normally would like to. Yeah, whatever, right? All right. Let's try see if we can squeeze one more in here. On that problem, what we did was we took the successive derivatives, right? We plugged in 0, and we found actually what c sub 0 was, c sub 1, c sub 2, c sub 3, right? But generically speaking, what we have is that, the power series now, that used to be c sub n out here, right? That used to be c sub n. We could actually just replace it with that formula right there. It's the nth derivative at a over n factorial, right? That is our new c sub n for this whole process. So let me give you this example. Let's say that you have f of x. You know what? I don't think I'm going to rush through this. I don't feel like rushing through it. So this is a more abstract idea. When you get your so we're going to pause, okay? We're not going to go to another example. When you go to your calculator and you type in like sine of 2, right? Like what is your calculator doing, right? It has no idea what the sine function is, right? So what your calculator is doing is it's using the formula x minus 1/6 or 1 over 3 factorial, 1/6. I'll leave it as factorial, 3 factorial. X to the third, and then plus 1 over 5 factorial, x to the fifth, minus 1 over 7 factorial, x to the seventh, plus dot, dot, dot. So when you type in sine of 2 on your calculator, what it's doing is it's just replacing all the x's here with 2's. And it's going 2 minus, what's that, 2 cubed right? 8 over 3 factorial, so 8 over 6, we reduce that fraction. But then here they do 2 to the 5th power over 5 factorial, whatever that is, and then subtract this, 2 to the 7th over 7 factorial. And what's going to happen is that this is going to converge to a number. And the number is what the calculator spits out. And whoever programmed your calculator, right, Texas Instruments, right, somewhere in there they have predetermined how far to go out into a series because they can't go forever, right? So they might go the first 20 terms of the series and then spit that answer out. And then you can go into your mode, your settings, and you can say, hey, give me more digits, right? And what that does is it tells your calculator to go further out into the series. That way it can give you more precise answers.
I guess it would be
Yeah.
slow if you went too far out.
Yeah, if you went out to like 1 trillion terms, then that could bog your computer down, right? But that's it. That's what's happening. Your computer only knows how to do, or your calculator only knows how to do what? Add, subtract, multiply, divide. That's pretty much it. Powers, right? Powers is multiplication. So you have like the 4 arithmetic operations. It has no idea circles and right triangle. It has no idea, right? So if you look at this, this is all just arithmetic, right? This is all either addition, subtraction, multiplication, or division. That's all it is. So your calculator can do that, right? And all happening at once, yeah. So, and it's fast, right? So, I'm not going to start a new example. I want to just see if there's anything in the notes here that I can address. Oh yeah, some notation. Let's just at least get this notation out of the way. I'm not going to write it down. It's in the notes. So in my notes, I actually go through the whole derivation of how we can get what C1 is and what C2 is. And then you basically come to a point where you have a generic formula. Right, there's my table, and then I say, finally at the end, we get this master formula for C sub n, right? And then what we can do is we can go back to our original formula for power series, and we can replace the C sub n with that formula, okay? This new formula right here has a name. It is called the Taylor series of the function at A. So if you give me a function and you ask for the Taylor series, that's what we're looking for. So with the Taylor series, this A can be anything. The examples I gave you, what A was I using?
0.
I was using 0, right? That is a special case of Taylor series where A is 0. We call that a Maclaurin series. So let me show you the definition of Maclaurin. A Maclaurin is that same formula we just had, replacing A with 0. So you know how this formula said you take the nth derivative at A? Well, with Maclaurin series, we're saying that that is 0 in there, always, for Maclaurin. And then over n factorial, and then here, instead of x minus a to the n, since a is 0, it just becomes x to the n. So Maclaurin is a specific case of Taylor when a is 0. Yes?
So I take it the reason that you wouldn't always do Maclaurin is some functions probably aren't defined.
Yeah, exactly. Good. You're seeing that perfectly. So if I gave you this function 1 over x, could we do a Maclaurin series here? No. You can't center that at 0 because it's not defined at 0. So you do a Taylor series, and what that would do is shift you off the asymptote, and then you could go find its Taylor series, shift it over. So the question would be, the series that we're getting, right? The series that we're getting, are they actually valid? Like, do they converge or diverge? And so we'd have to run a ratio test. On that, or like I should say, is there an interval where they're good? And there's some good news in this, and that is for the functions that we use a lot, like e to the x, it says here in our notes what the interval or radius of convergence is. You'll see infinity, infinity, and infinity for e to the x, sine x, and cosine x. All three of these really, really nice functions, that power series is convergent everywhere. So it doesn't matter where you start, you can shift it anywhere you want. If you start drawing the power series, it will map itself to the sine or cosine functions.
Could you use a limit set x as equal to 0, and then just do the limit at the end? That way you could always just stay on the point.
You mean let A approach something?
No, on, yes.
Yeah, because you're saying like on this one right here, you'd say, okay, I can't do the Taylor at 0, so let me do the limit.
Yeah.
I suppose you could, but I think the easier thing would just be do it at 1. Do the Taylor series at 1.
Yeah.
And then you can just avoid it, right? And you can look at the interval convergence to make sure it works, but even if you come up with a function, it's never going to be defined as 0. Like, if that function is not defined as 0, the one that you get that's supposed to be like that one should also not be defined as 0, right? So, all right, everyone, you have a weekend, right? And there's going to be a final exam. Did we talk about when that was?
Yes.
It's Tuesday. Is it Tuesday?
Tuesday at 11.
Not next week, the week after, right?
It's Tuesday.
Okay. It's 11?
You told us.
Okay. Have a good weekend, everyone.
Everything Taylor did.
What's that? What?
Taylor put all this work in the very beginning. And then when the form come afterwards.
I don't know. Yeah, I don't know why. I don't know why there's different names on it, you know?
Their names are always tied together. Taylor really did the bulk of the work. When?
There's probably some historical thing that I just don't know about.